structures, and it is a part of my PhD dissertation. So this is the outline of my talk. I'll give a brief on topological insulators and why they are necessary for spintronic applications. Growth of topological insulators, that is TIs, using sputtering. That's what I have done, and people in my group are continuing. And then the discovery of a novel antiferromagnetic topological insulator interface phase in topological insulator ferromagnet heterostructures. The effect of crystalline structural disorder of the TI in these in the magnetic properties of these TIFM heterostructures and interfaces. And if time permits, I'll present some work on low temperature magnetic insulator growth on topological insulator. So topological insulators, as we know, what is topology? Topology is a branch of mathematics which deals with geometrical shapes. And based on the topological equivalence, a certain object with a certain number of holes are equivalent. So a ball is equivalent to this wine cup because they do not have any hole in it, and the genus is 0. Similarly, a coffee mug and this donut are topologically equivalent because they have a single hole in them. And we cannot transform from one topological object to another without an energetic deformation. And this is what was found to govern the band structures of topological materials in reciprocal space, rather. So a topological insulator, when there is no time breaking reversal symmetry break, time reversal symmetry breaking magnetic field is present, we have a Dirac cone in the band structure, which gives rise to surface, topologically protected surface states. And in presence of a magnetic field, this time reversal symmetry is broken and the gap opens. And we expect a chiral quantum anomalous Hall state to be present. Topological insulators have not just been predicted, and the band structures have been observed using RPIS, and it's an established fact now. And the topological property in these topological materials arises because of spin orbit coupling, and which is the property which is of interest to the spintronics community. Topological insulators have been shown to possess very high spin to charge conversion efficiencies. And this has been mainly demonstrated using bismuth selenide through multiple experiments in literature. And the converse of spin Hall effect, which gives rise to the spin orbit torque in these cases, is inverse spin Hall effect, which has also been observed. So when we have a magnetic material placed adjacent to a heavy metal or a topological insulator with a large spin orbit coupling, the excitation of the magnetic layer causes spin currents, and which gives rise to non-equilibrium density of states in non-equilibrium spin density of states. And ultimately, what we see in ferromagnetic experiments is an enhancement in Gilbert damping, and which has been shown in topological insulators as well and attributed to the topological surface states. Now, we first grew topological insulators with varying levels of crystalline disorder using sputtering, and which was quite an achievement because the topological insulators with layered van der Waals structure using sputtering has been an elusive property. Most of the studies were done before us using MBE. Now, we looked at what is the effect of this crystalline disorder or improvement in crystalline ordering of the topological insulator. So first we looked at YIG, which is yttrium iron garnet coupled with bismuth telluride, which is the material that I have studied. And we see this clear enhancement in Gilbert damping when we have a C-axis oriented bismuth telluride compared to an amorphous bismuth telluride. And this is clearly either an effect of the bulk spin orbit coupling or the surface states. But of course, it is hard to separate the two in these experiments. In addition to the enhancement in Gilbert damping, YIG is a magnetic insulator. So a coupling of a magnetic insulator with a topological insulator can also cause changes in the gyromagnetic ratio, which we also observed. So this is very likely the surface states. Then we looked at various ferromagnetic materials. Here I'm presenting permalloy, which is nickel 80 iron 20 alloy. And here also we see that with this enhancement in C-axis oriented topological insulator, which I have named CBT here, there is this large enhancement in Gilbert damping and also changes in magnetic anisotropy. So further, when I studied topological these permalloy with bismuth telluride, a strange property started emerging. The saturation magnetic field, we started seeing this reduction in saturation magnetic field by almost 35 to 40%, and it is repeatable in every case. So we looked at these three different crystalline disorder in topological insulators, and what we also saw was that with increase in C-axis, increase in disorder in the topological insulator or higher amorphous quality of the topological insulator, this reduction in magnetic field was going down, as you can see this inset here. So this was a very interesting property, and we started exploring this more. So now surfaces are very interesting. So Pauli once said, God made solids, but surfaces were the work of the devil. And surfaces have all the interesting properties in them. So I looked at different literature reports on topological insulator surface reactions. And it seems that the topological insulators are, the surfaces of the topological insulators are excellent catalysts for hydrogen evolution reactions. So this is one indication that surface reactions are happening there. Further, few reports on bismuth selenides, they show that there is interfacial diffusion going on when you couple bismuth selenide with magnetic and non-magnetic metals. So we also looked at our sample with bismuth telluride, and it seems that there is a very selective nickel diffusion happening here. And why this is interesting is because nickel bismuth telluride, if we can find this compound, NiBi2Te4, it has a potential of housing quantum anomalous Hall effect. And why nickel bismuth telluride is more interesting than the selenides is that we can see the bond strength in selenides or sulfides are much higher compared to tellurides. That means in tellurides, we have a higher probability of electron hopping, which gives rise to these interesting magnetic exchange interactions and emergence of magnetic phases. And we can see that the exchange interaction energy is much stronger in the tellurides. So further, what is the implication if we see this 1 to 4 phase? Topological insulator doped with magnetic materials have experimentally demonstrated quantum anomalous Hall effect, as you can see from these reports. And there are numerous others. In addition to that, manganese bismuth telluride has also shown quantum anomalous Hall effect. And manganese bismuth telluride is in the same family of compounds as nickel bismuth telluride, and which is a highly explored material since last 1 or 2 years. So what do we expect? When we have a antiferromagnetic phase coupled to a ferromagnetic phase, we should see this exchange shift of the hysteresis loop. which is called exchange bias. So since nickel bismuth telluride has been predicted to be antiferromagnetic with a large exchange interaction energy, we would expect an exchange shift even in our samples. So we went down to 6 Kelvin, and we can very clearly see that there is a large exchange bias, about 80 Oersted exchange bias we observed in bismuth telluride. This, of course, varies from sample to sample, but the variation is not too large. It stays in the ballpark of 70 to 80 Oersted. And with field-cooled measurement, the exchange bias is much larger. And this is probably because of higher ordering in the antiferromagnetic interfacial phase when we have a field cooling. And this field cooling was at plus minus 1 Tesla. Further, the M of T relationship shows that there is a large Néel temperature of 63 Kelvin, which means that this has a potential of higher temperature quantum anomalous Hall effect. Now, how can we confirm that it is this interface, nickel bismuth telluride interface, which is the antiferromagnetic phase, for which we utilized polarized neutron reflectometry in Oak Ridge National Lab. So the beauty of neutrons is that neutrons also possess spins of plus minus half. And since they do not interact electrostatically, they can penetrate deep into the materials. And just like XRR, we can look at structural plus magnetic properties and depth-dependent magnetic properties in materials, because the neutrons interact with the the magnetization. So we looked at, for this particular sample, or this particular set of samples, we looked at 7 Kelvin temperatures, 0 field cooled, and 2 different bias fields of 1 Tesla and 5 millitesla. What we clearly see is that at 1 Tesla, we see an increase in the magnetization in the nickel bismuth telluride layer. At 5 millitesla or 50 Oersted, it's almost 0. That means that at low fields, it is transforming into an antiferromagnetic orientation, which causes the magnetization to be compensated. And we confirmed that it is this interface which is antiferromagnetic. Further, we performed yields and XPS measurements. And what we clearly see is that, first of all, using XPS, we see a signature of nickel chalcogenide bond formation, as we can see from this shift in the satellite peak. Further, yields also showed signatures of bond formation. That means there is nickel tellurium bonds forming there in the interface layer. When I looked at the selected area diffraction, it's something very interesting started emerging. There are additional peaks in the diffraction pattern compared to the bismuth telluride layer, which is the reference layer. And we looked at different compounds, different possible compounds forming, using first principles calculations with Professor Arun Bansil's group in Northeastern. And along with the first principles calculation, I also looked at, I also compared the diffraction peaks with the theoretical diffraction peaks of nickel bismuth 2 tellurium 4. And what is very clear is that there is a high possibility of nickel bismuth 2 tellurium 4, because the relationship is very linear with a slope of 1 and intercept almost an order of magnitude lower. So there is definitely a possibility of nickel bismuth 2 tellurium 4 present here, in addition to other phases also as marked here. And this is because it's a disordered interfacial layer. There is possibly more happening here. It's quite a dirty interface. So what happens if when we have a crystalline disorder in topological insulators? In presence of crystalline disorder, the topological properties are expected to still remain, um, but it has not been explored quite significantly enough. There are some studies like this group, they studied RPS they studied the band structure of disordered or amorphous bismuth selenide using RPS, and it seems that you still have this Dirac-like bands at the surface present. So when we looked at the same material system or similar material system with the higher disorder in topological insulator, bismuth telluride, we can see that there is still diffusion happening, but the diffusion profile changes. There is a higher depth of diffusion of nickel in case of these disordered bismuth telluride samples. But the surprising thing is that even though the diffusion profile or the diffusion depth is higher in these disordered topological insulators, the reduction in magnetic moment is not translating to the same level as the C-axis oriented topological insulator. So we think that it is because even though there is higher diffusivity and higher diffusion, not all the bismuth telluride is reacting with the nickel, with the diffused nickel, which ultimately gives rise to this reduction in magnetic moments. Because in this case, nickel is transforming into a different ionic state or different valence state. But what's interesting is that with increase in disorder in topological insulator, there is a reduction in the exchange interaction strength. What we see is that the exchange bias is much smaller in the amorphous bismuth telluride. And in addition to that, the Neal temperature also goes down to 20 Kelvin from 60 or 63 Kelvin in more C-axis oriented topological insulators. But the interesting thing is that this interaction and this interface, the antiferromagnetic interface still is present in a disordered topological insulator. That means reactions are still happening, and which predicts towards, which points towards the surface states, the topological surface states still being present, which are promoting these surface reactions. Now, I'll talk about my work on low temperature growth of magnetic insulator and topological insulator and similar lines of experiments. Now, why low temperature magnetic insulator are important? Since magnetism is a very quantum effect, when we have a magnetic material in adjacent to a material with high spin orbit coupling, again, there are signatures of proximity-induced magnetization in these materials. Now, in topological insulators, when we have a magnetism present, that gives rise to breaking of time reversal symmetry. And this breaking of time reversal symmetry should give rise to, or should allow us to explore quantum anomalous Hall or action insulator states. Now, there is only one particular material system and one particular study which has experimentally shown quantum anomalous Hall state using proximity-induced magnetization. Even though proximity-induced magnetization has been demonstrated using polarized neutron reflectometry as well as transport measurements in numerous studies. So for this, we need a sandwich structure, a magnetic material, topological insulator, magnetic material structure. But these quantum anomalous Hall states are only seen at extremely low temperatures. This was done at 0.03 Kelvin. And this is because the materials which we that have been explored till now, for example, this zirconium chromium telluride, they have a very low Curie temperature of about 40 Kelvin or something. Similarly, europium sulfide here in this study has a low temperature, Curie temperature of 17 Kelvin. So that means to achieve quantum anomalous Hall effect, which arises at much lower temperature than the Curie temperature, we need material which is magnetic at higher temperatures. But the problem is that the magnetic materials which can be grown or which are magnetic at room temperature, for example, using high vacuum deposition processes, they require very high processing temperatures, about 600 to 800 degrees Celsius. And at these temperatures, the topological insulators undergo phase change and are unstable. So we cannot grow a sandwich structure with those magnetic insulators, for example, YIG. So, but there is one solution, which is spin spray ferrite, which, even though this is quite a crude chemical deposition system or chemical growth process, but still you can grow magnetic insulators at low enough temperatures of 90 to 100 degrees Celsius, which you can expect the topological insulators to remain stable structurally and chemically. But the problem with this spin spray ferrite growth is that this is not a vacuum deposition process, so you have to expose the topological insulator to the atmosphere. And topological insulators, they oxidize very fast, more than conventional semiconductors or other materials. The native oxide is, the native oxide growth is also quite thick. And as I explored, this native oxide which forms on the topological insulator surface is impervious to coherent spins. That means there is no Gilbert damping enhancement that we observed. And also, there was no diffusion and reaction, which we expect with permalloy. And as you can see here in the hysteresis loops, there is no exchange bias observed in these when we have the topological insulator oxidized and a magnetic layer grown on them. So how can we prevent that? I looked at two different materials before, aluminum and titanium. Here I'm presenting the result from the titanium sample because it is more interesting. So with titanium interface engineering, since titanium has a low spin orbit coupling because it's a lighter material, even in case of titanium oxide, it's both light materials and both have a low spin orbit coupling. And these materials, titanium as well as titanium oxide, are highly transparent to spin currents. And what we can see here is that there is a large Gilbert damping enhancement, even in case of thick titanium oxide layers. With a 1 nanometer or a dusting layer of titanium, there is still a large interfacial diffusion happening. And we can see that the magnetic moment reduces, just like a control sample of bismuth telluride without titanium and then permalloy grown on them. But with a higher thickness of 2 nanometer and higher, this diffusion is completely blocked, but the large Gilbert damping enhancement still remains, which means that there is an effective spin pumping property still present in these topological insulators capped with titanium oxide. When we look at the hysteresis loops at low temperatures, we can very clearly see that this 1 nanometer titanium barrier, it still has a large exchange bias. And the exchange bias reduces a little bit compared to no titanium insertion layer samples. And this is quite expected because we are increasing the distance between the antiferromagnetic and the ferromagnetic layer. But with higher titanium barriers, since there is no diffusion, there is no antiferromagnetic phase forming, and there is no exchange bias. Then I drew nickel zinc ferrites using this spin spray method or spin spray process on these topological insulator capped with titanium or titanium oxide rather, because they were oxidized. And what we clearly see is that with this dusting titanium layer, there is a disordered interface forming. And the EDS data shows that there is high amount of iron diffusion because it's ferrite, it's iron rich. Nickel is a very small percentage here. And with this increase in titanium barrier layer, the disordered titanium interface becomes lesser in thickness. And
Nirjhar, you have 5 more minutes.
Sure, thank you. And what we also clearly see is that comparing the concentration of iron on the two sides of the titanium oxide barrier, we very clearly see that the iron concentration reduces with this increase in titanium oxide thickness. With this also increase in titanium barrier, we very clearly see that there is a reduction in Gilbert damping, but as we expect from a magnetic insulator coupled to a topological insulator, there is a finite change in gyromagnetic ratio, and which is extremely large in case of the 1 nanometer dusting barrier of titanium. What we also see is that with increase in, with reduction in temperature of measurement, we see a small exchange interaction. And this exchange interaction, we think, is because of iron reacting with the bismuth telluride in that disordered interface layer. With this increase in the barrier layer, we do not see any exchange bias happening anymore because there is no antiferromagnetic phase emerging. So these are my conclusions. We demonstrated the growth of topological insulator, highly C-axis oriented using sputtering. I demonstrated giant enhancement in spin pumping with this C-axis oriented growth of topological insulator. This was never explored before. The effect of crystalline disorder of topological insulators on spin orbit torque or rather spin pumping in topological insulator ferromagnetic heterostructures. Observation of antiferromagnetic topological insulator phase in commonly studied topological insulator ferromagnet interface. A degradation of the interfacial magnetic topological insulator exchange interaction because of the degradation of the magnetic insulator phase here in disordered topological insulator, and protection of the topological insulator surface or interface engineering using topological titanium oxide capping layer, which enables us to grow low temperature spin spray magnetic insulators on topological insulator. And we can explore the transport properties for interesting topological properties in these heterostructures in the future. So these are, they are my collaborators who have enabled all these experiments, who have helped me and guided me throughout my PhD and to help with all these interesting experimental results. And my research was funded by Northeastern University, the Army Research Office, the NSF, and PAMS. And I'm open for questions.
Thank you, Nirjhar, for the nice talk. As the speaker said, if you have any question, unmute yourself and ask away.
So yeah, I have a question.
Ask away, sir.
Nirjhar, excellent talk. I really enjoyed it. See, I'm asking about this antiferromagnetic, this interfacial state. Typically in antiferromagnetism, there is always entanglement because 1D material has been shown to be an entangled state because spin singlet. So 1D case was shown from our, by our colleague Professor Chiranjeev Mitra, Aisha Kolkata, and you could describe it using this singlet pairs, and it very accurately fitted. It's a 1D material. This, I think, copper, water, and a big chain. Big, some kind of a chain molecule. But in 2D, have you looked at susceptibility versus temperature and magnetic field?
No. I have only looked at the magnetic properties.
Okay.
Our research group is now studying transport properties, but we have not looked at susceptibility yet. I think we can because our squid does measure AC susceptibility. Yeah, I will keep you in the loop if we see anything interesting.
Sure. I'll forward you the papers of Chiranjeev. See, their susceptibility measurement was done in Germany because that was the early phase of Aisha. And it showed, it showed both through concurrence. There was some calculation for 1D material, susceptibility of concurrence. And it showed both concurrence and discord, the so-called quantum discord. So I'll forward you those papers.
Yes, please. I would be very excited to look at those. Thank you.
Okay, so if anyone else has any other questions, please ask. Okay, so let's thank the speaker for the talk once again, and also thank you for having me moderate these talks. It's been a pleasure. And I think there is a break now till 8 p.m. IST. So I'll be leaving, and let's see you guys.